to give a proof of it. So 17.8 proof of Stokes' theorem. The proof that's given in the book seems to me to have something a little bit wrong with it. At least the last time we looked at it, it seemed that there was some error. So just like a notational error. So but the proof I'm giving now I hope should not have any error. So here's the statement of the theorem. Let f of x, y, z be some C1 vector field. So M N R be, let this thing be a C1 vector field defined on an oriented surface S with boundary C. Let R be a parametrization of C that orients the surface consistently with S. Okay, so that's like this, right? If you have this hat here, and the normal vectors, the orientation is chosen so that the normal vectors are pointing out of the hat. Okay. Then you want to orient your boundary in this way, so that when you're walking on it, the positive side of the surface is on your left. Okay. The positive side of the surface is on your left. Then the circulation around the boundary equals the integral of the curl over the surface. The integral of the curl over the surface. We also wrote this as this dot ds r. It's the same thing. So right, this is this thing on the top here is the definition of this thing on the bottom. The flux of the field. The flux of the field over the surface is the same thing as the integral of the flux, the integral of the curl dotted against the normal vector over the surface. That's just the definition. Okay, so that's the statement of the theorem, and the proof of it. We're going to do it. We'll do this in one case. In the case of where S is the graph of a C1 function, little f, over a bounded planar region, D. Okay, so the picture is like this. You have some planar region. You have some planar region D, and you have some function, right? Some function f going from D in R2 to R. right? So to each point on D, it associates a height, right? And so we're looking, our thing will be the graph of f. So this thing here is x, y, z in R3, such that z equals f of x, y. Right. S is going to be the graph of f. And let me put some notation. So R, remember R is a parameterization of this thing. Right? Here's the boundary C, and then we have R is a parameterization. So R goes from some AB. R goes from AB to this thing, to the boundary. And here, let R0t given by x, y be the parameterization of the boundary of D obtained by projecting RT onto the xy plane. Okay, so yeah, I'm sorry. This the proof is not going to be the most exciting proof. So if you I see several of you have your hands resting on your heads resting on your hands. That's probably a good place for it. That's okay. Yeah, it's not. I'm afraid it's not the most exciting. It's just a calculation, but it's, you guys should see it. Okay. So so just notation, right? We have the graph here. Our surface is a graph. We have R, which is the parameterization of this thing, and then we project R downwards, right? We project R downwards, and we get this guy R naught. Okay, so R naught, right? So, right, let's say that RA is here, right? RA is here, and it goes around, comes back to RB. R naught is going to do the same thing on the boundary of D down here, right? So this is going to be R naught of A. Right, so it's the projection, right? It's the perpendicular projection downwards of this guy. Okay. So in other words, R of t could be written as x of t, y of t, f of x of t, y of t. So R naught here is this x of t, y of t, x of t, y of t. It runs around the boundary down here, and then R is going to be x of t, y of t, and then f of x, y of t, f of x of t, y of t. Okay, everyone okay? Everyone following? Okay, great. Okay, so so this part is R naught of t, and this part is f of y naught. Okay, so all we need to do is do a calculation. The proof is just a calculation. It'll be a calculation, and then use an application of actually Green's theorem. So we need to see that this is equal to this, and so let's just calculate. So so calculating the right-hand side. So right, we parameterize capital S as phi of xy equals xy f of xy. It's a graph, so we have a natural parameterization. Then, as usual, you get 1, 0, f sub x. Right? Differentiate everything with respect to x. Take the tangent vector along the y, in the y direction. And then we want to get a normal vector. So we take a cross product, and we get so we get so negative f sub x, and then negative x y, xy, and then we get 1. Right? And that's good, right? That's the upwards normal. Is that mine? Is that you? Need something? Okay, so then we calculate the integral. Right? What do you get? Right, the curl dot the normal vector ds over the surface. Right? So you get the integral of writing out what the definition is, you get the integral of over d of this dotted against negative f sub x xy, negative fy xy 1. Okay? Right. Remember that f was m and r, right? And so when you take the curl, you're going to get when you work this out, what you get is negative r sub y minus n sub z fx y x1 minus m sub z minus r sub x fy xy plus n sub x minus m sub y 1. Because when you take n and r, you see what you get. Right? You're going to get r sub y minus n sub z. Right? So r sub y minus, you get r sub y minus n sub z, r sub y minus n sub z. You get negative r sub x minus m sub z. And you get n sub x minus m sub y. Right, that's the curl. And then you take the Oh, you just, this is just you about. Properly, I should probably put the r of xy in each of these places also.
So
This is where you're about. This is the
Okay.
point of evaluation. I've left it out down here because I don't want to keep on writing it. But
makes sense.
yeah, but you're taking the curl at this point. Right? Yeah. So really, I should write r sub y at r of xy and a sense of z at r of xy, etc. etc. Okay. Any questions? This all we're doing is just the calculation. You see what it turns out to be, right? This integral turns into this thing. Okay. And then we'll do the other side of the integral, and we'll see that it turns out to be the same thing. Okay. So I don't know. I don't know. Do people want to see it? It's not the most exciting thing. Some people are shaking their heads. Well, actually, this is the more interesting part, I'm afraid. So we'll do it. It's the more interesting part because we actually have to use green. We have to see how Green's theorem comes into it. So okay, but yeah, okay. There's no way around it. Okay, so here's the left-hand side. You say, okay, well, f dot dr, that's of course the integral from a to b of f of r of t dot r prime t. Remember what r was, right? R is this thing. Right. So r prime, right? R prime t is going to be x prime t, y prime t, and then the derivative with respect to t of this thing, f of x of t, y of t. Okay, which by the chain rule works out to be f sub x. You need to take the derivative of this guy. Right, so you've got this function which depends on x and y, and those guys depend on t. Right, so again, you use the chain rule. Take the partial of f with respect to x and evaluate that at r naught of t, right? And then you multiply that by x prime t. Plus x of y, r naught of t. Y prime t. So putting that all together, remember our notation for f was m and r. So this turns out to be m of rt times x prime t plus n rt y prime t plus r at rt times that thing, right? F sub x r naught t x prime t plus f sub y r naught t y prime t. dt. Okay. Hey, it'll only take another 5 minutes. So hang in there for another 5 minutes, and then we'll be through it. Okay. So at this point, we're going to group things together based on whether they have x prime or y prime. Okay. So we'll have M. And we have this R of RT, F sub x, R naught T, all this times F prime T, plus the other guys with Y. So N of RT plus F sub Y, R naught T, Y prime T. So this is where we pass from the three-dimensional integral, from the integral over the curve in space to the integral on the ground. Okay, so we're going to drop down to the ground, and we're going to apply Green's theorem, and that will give it this. Yeah, Lily.
Will there still be an R of RT next to the Y?
F sub Y, R
Would
naught.
that still be multiplied by the R of RT?
No, this is F sub Y evaluated. Right, it's from
Where
here.
did the big R go?
It's right here.
Well, how come it's only multiplied by?
Oh, thank you. Yeah. Thank you. Yeah, there should be an R. Sorry, I thought you meant little r. Sorry. Yeah, thank you. So R T F sub Y. Okay. Okay. So at this point, we're going to define a function on the ground. Okay. So let capital F twiddle xy be. You should always laugh at that. Why is the word twiddle funny? Twiddle. I'm not sure. Okay. But this is what mathematicians call this symbol, twiddle, or tilde. Tilde? Okay, maybe I'll say tilde, just to avoid any humor. Okay, so let f tilde xy be m of xy, m of xy, f of xy, plus r of xy, f of xy, s of x, xy, comma, n of x, xy, f of xy, plus r of xy, f of xy, x of y, xy. Okay, so this is a vector field. This is a vector field on R2. Okay, so a vector field. So what we're doing is basically we're going to change this integral over a vector field on R3 into an integral of a vector field on R2, and then we'll apply Green's theorem to it. Okay. So so then this thing down here we can rewrite as the circulation around the boundary of D of F twiddle against dr naught. F tilde against dr naught. Right, so you see what we're doing. Right, we have, here's our D, and here's our C. Down here is delta, right? And here is, up here we had R, and down here we have R naught. From A to B, right? And what we're doing is we're taking the integral, the circulation of F around this thing, and we're recognizing that actually we can express it as the circulation of this field around this guy down here. Okay, we're just cleverly rewriting it. Okay, we rewrite it as the circulation of a field on the boundary of the domain down here. Okay, everyone all right? It's not exciting, but it's effective. It will be effective. Okay, so from there we can apply Green's theorem. Right, we're talking about the circulation of the field in R2 now, around the disk in R2, and so we use Green's theorem. Right, so by Green's theorem, we get that our integral down there turns into the double integral of ddx, right? Ddx of the second guy, right? And xy f xy plus r xy f of xy f sub y f sub y xy. Minus ddy of mxy f of xy plus r of xy r of xy f of xy f sub x xy dA. And then, maybe I don't want to do this last part, but when used as a chain rule, you use the chain rule again. Using the chain rule, you get that when you take these derivatives, what you get is that this sums to n sub x plus n sub z of x plus r sub z. 1 r sub x fy minus m sub y minus m sub z fy minus ry x, which is what we wanted. So the I think the main thing I want you to get out of this is this transfer. Okay, is this transfer? Don't worry too much about all the calculations, but I'd like you to understand how we go from here down to here. Right. This is really the key thing, to recognize that this integral, the circulation around this curve in space, can be dropped down onto the circulation around this curve in the plane, right? And then you apply Green's theorem to it, and it turns out to be the same. Okay, that's it for that. Okay. Okay. So okay. So So the very last thing we're going to talk about in this course is something called the divergence theorem. Right. So Green's theorem, I'm sorry, Stokes' theorem talks about relating the flux through the surface to the circular. I'm sorry. It talks about relating the integral of the curl over the surface to the flux of the curl through the surface. Sorry. To the circulation of the field around the boundary, right? So you might think, by analogy, that there should be some sort of flux divergence form, right? You remember how Green's theorem had the circulation curl form, right? The circulation can be expressed as an integral of the curl, right? And it also had the flux divergence form, right? So just now, Stokes' theorem is basically a circulation curl form. Right, you're talking about the circulation of the field around the boundary, and you can express it as an integral of the curl, right, the flux of the curl. So by analogy, you might expect that there should be some sort of flux divergence form, and that's the last thing. It's called that's the last part of the course. It's called the divergence theorem. So maybe I'll just state it, and then next time I'll just state it, and then we'll take our class photo, and then next time we'll do some examples. So here it is, 17.9, the divergence theorem. So the analogy is that Green's theorem has two forms, right? Circulation curl, and it also has the flux divergence form, which you get by turning the circulation curl form sideways. So here, in higher dimensions, we have Stokes' theorem, and there should be something here. And what is there is this thing called the divergence theorem. I think it's also called Gauss's theorem. So here it is. Let E in R3 be a simple solid region that is, and what we mean by that is a region that is simultaneously x, y, and z simple. So simultaneously x, y, and z simple. Let S be the boundary of E. The boundary of E. So this is the, so you have this solid region, right? Basically like a potato. A potato. The boundary is going to be the skin of the potato, right? Just the outer edge of it. Given positive orientation. Positive orientation means outward normal. Now, as usual, you need a vector field. So let F be a C1 vector field on an open region containing E. Then the flux of the field through the surface equals the integral of the divergence over the solid. The flux of the field through the surface, flux of the field through the surface equals the integral of the divergence of the field over the solid. Okay. So again, this will be some way of switching, you can change integrals, integrals over the solid into integrals over the boundary, or vice versa, integrals over the boundary over integrals over the interior. So maybe that's where we'll stop.